Hello, I'm just messaging Rich back. I just messaged him saying, uh-oh, it's not working. But now it is working. Hooray. I thought maybe it was just like too many people trying to do streaming at the same time. We're good. Today is the rest of differentiation. So for those of you who scrolled back to the beginning, this is a 45-minute session. 45 minutes is an action hour. If you work during the day, I strongly encourage you to work in, you've got to structure your own time now, right? Do 45 minutes and then you walk around. So I just finished my first year lesson and I went and got toast. There's the proof that I actually, and it makes such a difference. It's amazing how much of a difference it actually makes to physically stand up and move about. So being strict with yourself with the rules of the action hours during the day is going to really help you to keep motivated and get the most out of your study time at the moment. The exambulant, it contains everything that I'm going to be talking about. It's got the map of the A level. It's got the revision notes with the link to the videos which show you how to fill in the revision notes. It's got everything in the exambulant. So please share. It's not brown or white. It's rye bread. That's very yummy. Share the exambulant and let's just keep going, plowing on with the schedule that we set. Good. Okay. Yummy taste. It's really nice and it's got cashew butter on it. Okay. Timer. 45 minutes. Ready? Go. So here's the map. This is what we looked at the beginning of the week, and we talked about the different sections and like which bits you needed the most help with. And yesterday we looked at differentiation, and today we're going to look at differentiation again, but we're going to tie it all up. Okay, this is going to be totally finished. So in terms of a playlist for the next 24 hours, all of these will be available for free. We are going to be doing chain rule, product rule, quotient rule, and then these three: differentiating inverse functions, implicit differentiation, parametric differentiation, connected rates of change, because they are all basically the chain rule. Okay. What we did yesterday was the derivatives of all 10 things. Talked about inflection points, concave and convex sections of graphs to do with the second derivative. And I showed you some of the proofs of the derivatives, and I showed you where to find the proofs of all the other ones. I also made available the first principles video for trig. So for differentiation, sorry. So the playlist for the next 24 hours is these. And then that means that at the end of the 24 hours, we can go tick, differentiation is all done. Yes, we did proofs yesterday. I didn't prove all of them, but I showed you different ways to prove the derivatives. And all of the proofs of the derivatives are in video number 28. They're the ones that you need to know. What else was I going to say? Yeah, so by the end of today, we will be able to do all of this differentiation. And if you go in your exambulance, if you go in the revision notes and click on the title differentiation, it will take you into the lesson where we make the notes on differentiation. Okay, so if you want to make complete notes, then you can. T-Boy, are we covering mechanics? Yes, look at the schedule. So there's a schedule in the exambulance and that shows you when we're doing what. Okay. We are always, second years, going to start with some integration. Why is that? It's because it's the most important thing. In the second year, it's often left too late. It's not algorithmic and it takes a long time to get good at it. So we're always going to start with some integration practice. I'm going to give you, I think I'll give you a minute. No, that's too long. 30 seconds on each of them. Just have a quick look. They're all really super quick, these ones, and they're connected to what we're going to be doing today. So I'll give you 2 minutes starting now. Yeah, the top is 3x squared, sorry, yeah, not cubed. The bottom is x cubed plus 1, and the top is 3x squared. Okay, that was a minute. Please remember that what you should be doing is thinking in this direction. So you should be thinking what got differentiated. And whatever your answer is, if I differentiate your answer, I should get that thing. Kawai, if you mean this, then no, that is not true. It works the other way up. If I had x cubed add 1 all over 3x squared, and I did x cubed over 3x squared, and 1 is over 3x squared, that's true. But it has to be a V shape, not an upside down V shape. Okay, 15 more seconds. Just have a look at them. I have to do this, by the way, backwards, 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 because I can't press erase, otherwise it has a flip out. Okay, so I'm at the moment, I'm putting together a playlist about integration, okay? So to sort of teach you the way that I structure the blocks of making it slowly, slowly harder. So the first block that we do is integrating these things here, these 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So just for ages and ages and ages, the integral of tan x is given, but they could ask you to prove that the integral of tan x is that. They could ask you to explain why. Or they could do one of those questions where it says, this student has written this thing for why the integral of tan x is ln sec x. Why are they wrong? Or something like that. You know, so you do need, the tan x is one of the ones you need to just know. So stage 1 of the integration is literally cos, sine, sec squared, cosec squared, sec tan, cosec cot, a to the x, e to the x, 1 over stuff and stuff to a power, okay? The quotient rule is for differentiation, not for integration. This is the thing, there are no rules for integration other than parts, which we hardly ever need. So very first step on the playlist is just these things here, these 10. Then we move on to this sort of thing. Now, this sort of thing, these are all really, really simple if you think in that direction. If you don't think of it as integrating, always think of it as differentiating, then these are fairly straightforward. So none of these require any work, none of them. I'll show you what I mean. So I'm looking at a fraction. My number one thought with a fraction should be, is the derivative of the bottom on the top? That's number one thought. If the derivative of the bottom is on the top, then I know what the answer is. Actually, I should do a modulus sign, strictly speaking. There, done. Okay. Now I need to have a little think, obviously. If I differentiate ln x cubed plus 1, what happens? Well, the derivative of ln is 1 over. So the first thing that would happen is I get 1 over x cubed plus 1. But then the chain rule says I have to multiply by the derivative of the inside. Oh yes, plus c, you're completely right. So the derivative of the inside is 3x squared. So I'd multiply by that. So it totally works. It's completely perfect. And that's the end. Easy peasy. Right. Let's have a look at the next one. Now, I happen to know that the derivative of tan is sec squared. In the exam, the current mark schemes for the new spec do not penalise you for not using a modulus sign. That's not to say they couldn't in the future, but at the moment, if you put brackets here, it's sometimes really hard to see whether a student means brackets or modulus anyway. But at the moment, you wouldn't be penalised. The reason for it is that we can't do ln of negative numbers. That's not possible. So we have to make sure that the thing inside is going to stay positive. Oh, T-boys, straight on it. So good. The derivative of tan is sec squared. Now, don't forget, I am not thinking in that direction. If I try to think in that direction, integration is always going to be a wonder, a mystery, and a pain in the bum. What I am doing is thinking in this direction. What got differentiated it? What got differentiated it? What was differentiated? Right. I happen to know the derivative of tan is sec squared. So this is obviously the chain rule in action. What I obviously started with was this. Now let's think through differentiating. We pull the 3 down. Oh, I don't want a 3 at the front. There's no 3 there. So when that 3 comes down, there would be a 3, but there's no, so that's easily dealt with. We just go like this. Okay, thinking, pull the 3 down, it lands on the 3rd, it cancels, that just gives us tan squared. Brilliant. But then the chain rule says we have to multiply by the derivative of tan, and the derivative of tan is sec squared, which is why that's there, and that's the end. Perfect. So all of these are, there is no working required whatsoever, and yet in the exam, pages and pages and pages of working because of the way that students think about integration. So I'm really trying with this playlist to get you to think differently about integration, to get you to think, actually, there is no such thing as integration. It's all just a puzzle of working out what got differentiated. How did I get tan cubed? I just looked at it. So the structure of what we've got here, the first one is a really, really common structure that you need to be aware of. It's got a thing at the bottom and then the derivative on the top. And the answer to that is ln of the bottom. That's what got differentiated. The second one is another really common structure, and it's where I've got a thing, f of x, in this case tan, okay? Tan x is the thing in this case. I've got a thing, and it's to a power. So in this case, I've got tan x to the power of 2. And then sitting right next to it, here, is the derivative of the thing. There it is. That's the derivative sitting out the front. So it could be at the front, it could be at the back, but it's next to it, the derivative. And then I know what got differentiated because I know the chain rule. What got differentiated was that thing there, in our case tan, but to a slightly higher power. Okay. I'd need to do a bit of fiddling, right? Because the n+1 would come down, and so I'd need to maybe, like with this one, put a 3rd at the front, but that's the common structure. So there are these common structures that you need to look out for. There is one more. There are 3 of them all together. The other one is where you've got e to some function. Could be anything at all. Anything. E to the blah, 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 right? But same as with this one, there's its derivative. And same as with this one, there's its derivative. Same thing with this one. If you see the derivative sitting at the front there, then we know what the answer is. We know straight away what got differentiated. We don't need to do any work. What got differentiated was e to the f of x. Think it through. Okay, what's the derivative of e to the something? The derivative of e to the something is e to the something. And then the chain rule says that we have to multiply by the derivative of the thing. So if we differentiate e to the blah, 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 we get e to the blah, blah, blah times the derivative of the blah, blah, blah. And that's what I can see going on here. The derivative of x squared is 2x. Yeah, I'm going to have to do a bit of fiddling, but that's fine. Okay, equals. So I reckon what got differentiated, notice I'm leaving a little gap at the front for any sort of number I need to put in. What got differentiated is e to the x squared, I think. Let's think it through. Derivative of e to the x squared is e to the x squared times 2x. Okay, close, but I want 4x, not 2x. So if I put another 2 there, now it works. Okay, now this one doesn't look like it's any of those 3, does it? But it is. This one is. There's 3 main structures to look out for. A fraction, where the derivative of the bottom is on the top, something to a power, and then e to something with the derivative at the top. But it's always about being able to see that derivative. So knowing that the chain rule has been done. Okay. So exactly, sine over cos. Tan is sine over cos, isn't it? So this is sine x over cos x. Okay, we have a fraction. Thought number one is the derivative of the bottom on the top. Yes, it is. That means I know the answer. The answer is ln. Let's think about whether or not I need to do anything. Ln of cos x is 1 over cos x. But then the chain rule says we have to multiply by the derivative of the inside, which is minus sine, not sine, minus sine. So we need a little minus sign there so that when that minus comes out with the chain rule, boom, cancelled, gone, everything's fine. Now you might often see that rule of logs used. You might often see that become a power up there instead. In which case, instead of saying minus ln cos x, we could say ln of 1 over cos x, which is sec x. So this is usually how you will see the derivative of tan written, ln sec. But it's that process. You can do cot in the exact same way, okay? Exact same way. So we'll come back to this tomorrow. There was a good question from RD. Why do we do the chain rule if it's just a function by itself and not a function within a function? Now, this is a really good question because the whole point of today is for me to focus on the chain rule. Because as I hope you can see from these demonstrations, integration is all about the chain rule, weirdly. It's all about the chain rule. It's understanding the chain rule in a certain way and being super good at using the chain rule. That's really what integration comes down to. So I'm doing a little bit of integration at the beginning of every session to keep coming back to it and keep topping up and keep trying different skills. But today I want to focus on what's really, really important, which is the chain rule, okay? So here is a derivative for you. Things you need to know to do this derivative. Derivative of sine is cos, derivative of e is e, derivative of x squared is 2x. You do need to know the chain rule, which is basically that we pretend it's an x and then multiply by the derivative of the thing. And you also need the product rule because we've got two things times together. Thing one and thing two. Okay, I've also added a fun little challenge on for those of you who want to make it a little bit harder. Okay. Yeah, Ibrahim, I know what you mean, but I don't encourage the use of the word integrate. Okay, because if you think of integrate as a verb, to integrate, then it becomes a very, very, very difficult topic. If you think of it not as anything to do with anything other than differentiation, it's only a puzzle to find out what got differentiated, and it's one of 10 things. So it's literally every single integral I show you, if you think of it as I wonder what got differentiated, and there's only 10 things that could have got differentiated, literally. There's either sine, cos, tan, sec, cosec, cot, e, a to the, x to the n, and ln x, that's it, okay? Yeah, I know you're answering it, but the answer that you gave is typical of the way of thinking about integration that can cause problems. So I'm encouraging you to like turn your thinking round and look at that integral. And instead of thinking, I will integrate it, instead of thinking that, think to yourself, I wonder if I can work out what got differentiated. Okay. Right. You've got another 30 seconds to have fun with this one, and then I'm going to talk you through it. Meanwhile, I'll eat my toast. So what I'm going to demonstrate to you here is a way of using, we need the product rule first, definitely, is a way of using the product rule and the chain rule without using any U's or V's. Okay, that's what I'm going to demonstrate to you. We are basically doing the exact same thing that you've probably learned to identify U and identify V, but I'm going to do it in a way that doesn't actually specifically identify U, particularly for the chain rule. And I think that this, being able to do this, being able to use the chain rule without writing down U equals, not only does it make the chain rule a billion times easier, it also makes integration become a lot easier, because integration is essentially the chain rule. It's looking at something, fiddling around with it, working out what got differentiated, and almost certainly the thing that got differentiated was differentiated using the chain rule. So that's how it's all connected up. So here we go. The derivative dy by dx equals. Now this is how I think of the product rule. I've got 2 kids, right? I've got 2 daughters, and I would sometimes say, just wait while I help her. Just wait a second while I help her, and then I'll come and help you. And then when I've helped this child, then I would say, right, now just wait there. I'm going to help her now. That's what the product rule is. Okay. That's a good question. Yeah, I will come to that. So here's the product rule. 4x, I'm going to differentiate U. So E, be patient, just wait. I'll come to you in a minute. So there's the derivative of 4x, and this is the patiently waiting other function. Then a plus. Yeah, it is like I help my daughters, exactly. I literally think of it like that. You wait while I do you. Right, now. You wait while I do you. So now 4x is waiting while I differentiate this guy. Now, this is where I think the chain rule without U, just the chain rule in this way of describing it, is much, much cleaner and nicer. What we do is we just pretend that it's an x. And by it, I mean whatever you like. So it's just obvious if you don't overthink it. This says e to the, that's what that says, e to the. What is the derivative of e? It's e, okay? That's it. Which I'm just gonna do, the derivative of e is e. So the derivative is that. But the chain rule says I now must multiply by the derivative of the thing, okay? So now I have to multiply by the derivative of 1 minus sine squared 2x. Because I was lying, it wasn't e to the x, it was e to the some other malarkey up here. But I don't have to think about that until I'm ready to think about it. The derivative of e to the blah is e to the blah. Right now I'm thinking about that derivative. So 1, that's easy, that differentiates to 0. Now I'm looking at minus sine squared 2x. Okay, well, let's just think of it as something squared. Like literally, let's just think of it as blah de blah 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 squared. So how do we differentiate blah de blah 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 squared? We pull the 2 down and change it to a 1. Pull the 2 down, blah 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 blah, change it to a 1. That's the end. But now we have to differentiate the multiply by the derivative of the inside. So I'm moving the goal. I'm moving in. It's like Russian dolls moving in towards the answer. So the derivative of e to the was e to the, but then I had to multiply by the derivative of this. The derivative of this, oops, I didn't multiply. Oh yeah. So the derivative of this is pull the 2 down, change it to a 1. But now I have to multiply by the derivative of that thing that was squared, the sine 2x. All right, what's the derivative of sine 2x? The derivative of sine 2x is cos 2x. But now I have to multiply by the derivative of the inside. Done. Okay. Now, if you practice using the chain rule in that way, where you're not introducing, you're never ever writing down u equals, you're just always going in another layer and in another layer. If you practice that over the space of a couple of days, your chain rule is going to be so much stronger, and you will suddenly find that integrals like this don't seem difficult. That's why I'm saying to you, yes, integration is hard, but the reason it's hard is that you're not looking at things like this and things like this and things like this and seeing that the chain rule has taken place. So the problem is the chain rule, not integration. Okay, derivative of e to the is e to the. Now I'm differentiating this. The derivative of squared is pull the 2 down and change it to 1. Now I'm differentiating the inside. The derivative of sine 2x is cos 2x. But now I need to multiply the inside. That's the derivative of 2x. That's the answer. So how did I manipulate it? For those of you that were wanting to do the complicated thing, it's 4e, oops, just turned it off. 4e to the 1 minus sine squared 2x plus, what have we got? A minus and a 2 and a 2 and a 4. So that's 4 and 4, it's 16. So it's minus 16x. Then I've got sine 2x cos 2x. Then I've got e to the minus 1 minus sine squared 2x. So I'm going to pull out the 4 and I'm going to pull out the e to the 1 minus sine squared 2x. And then in the brackets, I'm going to have 1 minus 4x sine 2x cos 2x, which I think is where everybody got to who was trying that hard a bit. Okay. So, oh, frozen. Right. I am going to wait until you tell me it's not frozen. Maybe I should have a look on my laptop as well. I mean, my internet is fine. Yep. Yeah, let me put it in here. Keyboard. Yeah, I don't know why. I think we're okay again. Good. Okay, great. So, yes. So this is my, I did this deliberately. I set this one up deliberately because I wanted to point out to you a very, very common thing in exams. So if I asked you, what is sine 2a equal to? I reckon all of you would know. I reckon all of you would know that sine 2a is 2 sine a cos a. Tick. Right, but in this situation, I am showing you, hang on, I just want to try and see my screen so I know what I'm writing. In this situation, what we have here is sine a cos a. Yeah, I don't know. I'm just going to have to carry on and hope that the recording isn't buffery, okay? So sine a cos a. Think of it the other way round. So instead of thinking of it as sine 2a is 2 sine a cos a, think of it this way round. Sine a cos a is a half sine 2a. Now this is why I call these the double halves. The double half angle formula. Because what students learn is they only learn them in one direction. They learn that, I'm just going to carry on because I don't know what else to do really. They learn that sine 2a is 2 sine a cos a, but they don't learn that sine a cos a is a half sine 2a. So using that here, sine 2x cos 2x is 1/2 sine 4x, double. So instead of halving the angle, in the other direction, you double the angle. And that's why I call them the double halves, okay? So that's why it ended up like that. Right. I hope you guys can see this. See if you can have a go with this. I'll type them in. Right. I typed them in the chat just in case. Good, it's working. Excellent. I'm going to speed up a tiny bit because we lost a bit of time there. So I'm going to, instead of giving you time to work on these, I'm just going to go through. And again, what I'm demonstrating is that we can use the chain rule without introducing u, and that it actually makes more sense and helps us with differentiation and integration. So in this case, we get the derivative of e is e. And now we multiply by the derivative of the thing inside. Done. The derivative of e is e. And now we multiply by the derivative of the x to the 4. Done. The derivative of e is e. And now we multiply by the derivative of the inside. Done. Okay? It is just the chain rule. Implicit differentiation is equal to the chain rule. It's nothing different. It's the chain rule. What you do with the chain rule, the way that I think it helps to think about it, is pretend there's no problem. And then times by the derivative of the inside thing. Okay? So let's have a go at this one. How do we differentiate this? The 4x differentiates to 4. Now there's a minus. Now there's a product. So I'm going to use big square brackets around the product. You weight e to the y while I differentiate the 2x. Then a plus. Then you weight 2x while I differentiate e to the y. How do I differentiate e to the y? The derivative of e is e. So it's just e. But then the chain rule says we have to multiply by the derivative of the inside. So we have to multiply by the derivative of the y. And the derivative of the y is dy. That's what it is. So implicit differentiation is the chain rule. And the chain rule, when you think about it in this way, when you don't introduce a u, where you just have in your mind, and now I differentiate, it makes it so much easier. And it also means that you will be able to integrate really well. Now, there are two situations in which using the chain rule in that way is less helpful than using the chain rule written in this way. So the other way of thinking about the chain rule, which you may have learned, is that it looks like this. That is the chain rule. It is the same idea. What's happening here is that we're pretending there's not a problem. We're just differentiating it. So like here, let's say I was just differentiating cos 3t. I'd go the derivative of cos 3t is minus sine 3t. And then you multiply by the derivative like that. The way of thinking about it like that is that's the differentiation, and then you multiply by the derivative of the thing that really wasn't just an x. Okay, so this is the chain rule in its pure notation form, which is not that helpful for these situations, not that helpful. Not that helpful for these situations. Introducing a u actually makes it harder to use the chain rule. Not useful in these situations because you're so you're removing yourself from the structure of the chain rule every time you write u equals, which means that you can't then just spot these ones and see that the chain rule has been happening. But parametric and connected rates of change, it's not like that. It's actually easier to use this in this form. So parametrics, we are going to look at on Friday. But this is a set of parametric equations. And the set of parametric equations, we are going to differentiate the first one with respect to t. And we're going to get 3 sec t tan t. And then we're going to multiply by dt by dx. Now, what is dt by dx? Okay. dt by dx, we're going to use this rule here. dy by dx multiplied by dx by dy equals 1. Fact. That's the chain rule. The chain rule is what says that we can cancel these DTs, basically. That's what the chain rule says in a sort of roundabout, funny way that doesn't seem to make sense, but it is kind of saying that that DT and that DT cancel, so therefore dy by dx, this thing here is the same as dy by dt, dt by dx. As I say, not the most useful thing for doing the chain rule in real life, but for parametrics and connected rates, really, really useful. So the chain rule says that these two dx's cancel. Therefore, we get dy over dy, and dy over dy is 1. Now, if that is true, which it is, then therefore dx by dy is 1 over dy by dx. So the fact that we can flip them is just an absolute one step from the chain rule. It's just the chain rule. So where I've got here dt by dx, actually dt by dx is 1 over dx by dt. So instead of multiplying by dt by dx, I can divide by dx by dt. And this is how you will see it written. You will see, and this is how I teach students to do it as well, dy by dx is a fraction. On the top is the derivative of the y, and on the bottom is the derivative of the x. Nice and simple. Okay. Violet Star, have a look in the exambulance and have a look at, yeah, exactly, Anish. Have a look in the exambulance. If you go to the Tailored Tutors website, there is a free course called the exambulance, and in there is a schedule. It shows all the individual weeks, and it shows the point at which you are going to find out your calculated grade, and it shows you when the actual exam, if you don't like your calculated grade, is likely to be. The gap between those two is smaller than the gap that you had a week ago between real life and your exam. So we can't wait till then. On the other hand, you might get the grade you want, and doing 10 hours study a day is not necessary. So we're doing 1 hour a day, 1 hour first years, 1 hour second years. There's another study with me from 4 till 5 if you want to do another hour, just to keep everything ticking over to get the spec finished. You'll see it in the schedule. Okay. Right. So on the bottom here, now look, what do I need now? Chain rule to differentiate this guy. I don't want to be going off and introducing another u over here that's connected to the t's, that's connected to the x's, that's connected to the y's. It's going to be carnage. There's already too many letters. If I can just differentiate this using the chain rule, it's going to be great. So 2 comes down, changes to a 1. That's how you differentiate squared. The 2 comes down and changes to a 1. And now we multiply by the derivative of the cos 3t. The derivative of cos 3t is minus sine 3t. Derivative of cos is minus sine. Derivative of squared is pull the 2 down. And now we multiply by the derivative of the 3t. Okay, so the answer is 3 sec t tan t over, the minus and the minus cancel. We've got a 2 and a 3 that makes 6. We've got cos 3t sine 3t, which, as we know from the previous one, we can write differently. So maybe we might write our answer like this. Sec t tan t over, instead of 6 cos 3t sine 3t, I could write 3 sine 6t. So you should be able to see now how I made that move. I did the exact same thing down here with that doubly halfy as I was talking about. Where's it gone? Where's the doubly halfy? There it is. The same thing as I was talking about here, that if you've got sine A cos A, that equals a half sine 2A. Okay. Anush and Sarah. 2 things. 1, over February half term, I did all of the entire A level, first year and second year revision notes, and it took me 10 hours. So that's what's in the course. If you click on revision notes, those titles are hyperlinked into the course, and that is literally the entire A level revision notes in 10 hours. Now, you won't need to do most of that, but if you did 2 hours a day for 2 weeks and had 2 days off, that'd be the whole lot done. So that might be a lot quicker for you than what you're doing at the moment. 2, if you're being set homework by your school, what I would strongly suggest is that you do this. You go, let me just quickly show you, and then we'll go back into the thing that I was doing just there with doubly halfy angles. You go into the content guide. This is if you've got a subscription, because what I do the rest of today is I answer students' questions in here. So students go into the content guide. Say you've been given a question on, like, I don't know, second year. Say you've been told to learn moments because they didn't do moments, right? You can go into the moments one. You can click on any moments question. You can take a photo of your homework and upload it as a comment. There's probably some in here that I can show you. And then I can help you with it. So your homework's going to be a lot faster if you're able to just chuck a question up and get help with it. And the only 2 hours that I'm not sitting answering questions are the 2 hours that I'm on here, basically. So like this sort of thing. So you can just put in a picture of the question and then I can help with it. Okay. So that'll at least make your life a bit easier. Okay. Hopefully. Right. We've got 5 minutes left of our action hour and we're nearly done. So parametrics. Oh, one more thing. I don't know if anybody noticed, but look at this guy. Might be nicer rather than having sec and sine over cos. So that's 1 over cos and sine over cos. So it's sine over cos squared. Might be nicer to multiply the top and bottom by cos squared and just have sine t over sine 6t cos t. And that's the sort of thing that you'll need to be able to do. Not just use this rule, but also then incorporate in all of your trig to solve the problem. And this goes back to what I said right at the beginning of the week, that the red things are the most important, that actually when you are doing differentiation, you are pulling in all of your trig and all of your algebra. And when you do integration, you are pulling in all of your differentiation and all of your trig and all of your algebra. So the other things around the outside, they're kind of standalone, and the things at the bottom don't really matter at all in terms of the number of marks or how long they take to learn. But this block in the middle, if you're not super good on the trig and the differentiation and the algebra, then the integration is going to always be impossible to you. And I think a lot of students think that integration is hard, and actually the problem is here or the problem is here. So that's why I'm drawing you away from the integration to look into those two things. Right, last thing, connected rates. Is that my last thing? Oh, and arcsine. Right, I've got 4 minutes, so I'm going to show you how to do these. So the chain rule. This is situation 2, when I think it's more helpful to think of the chain rule as dy by dx is dy by du by dx. This is situation 2. It's where you've got connected rates of change. So we had time in this one, and we've got the volume, and we've got the radius, say. And we want to find the rate of change of the radius. We know the rate of change of the volume. It always forms this same triangle. Join up the bottom yourself. There's a formula connecting these two. Always, always, the bottom is joined by some rule that you're either told or you know. Then you can differentiate. And now we can use the chain rule. So the chain rule says dr by dt, that's what we want, is dr by dv, dv by dt, which is, now dr by dt, here it is, dr by dv is this upside down. We already discussed that, that's the chain rule. There it is, upside down. So dr by dv is 1 over 2/3 pi r, dv by dt is minus 0.1, and we're done. Chain rule. So this topic is called connected rates of change, but it's actually the chain rule. This topic is called parametric differentiation. It's actually the chain rule. This topic is called implicit differentiation. It's actually the chain rule. Last one, have I got time? I've got 2 minutes. I reckon I've got time. This is what we do. Y is arcsine x. Do not like that. Do not differentiate arcsine. No, we only differentiate sine, cos, tan, sec, cosec, cot, e to the x, a to the x, ln x, and x to the n. So let's do sine to both sides. Now let's differentiate both sides with respect to x. On this side, x differentiated with respect to x is 1. On this side, chain rule in our heads, implicit differentiation. Derivative of sine is cos. Then you multiply by the derivative of the inside. Let's make it dy by dx equals. Okay. Now, I happen to know, and I think you probably do too, that sine squared x is 1 minus cos squared x. So sine x is the square root of 1 minus cos squared x. So sine y is the square root of 1 minus cos squared y. So cos y is the square root of 1 minus sine squared y. And this is what I can use down there. Why is that helpful? Why would I want to do that? What was wrong with cos? It's because I need to use this guy here. Sine y is x. It said in terms of x. In terms of x. So it's no good leaving it as 1 over cos y. That's not in terms of x. But I've got all my trig, so I can use all my trig, and then I can replace this sine y here with x, and I get the answer. Boom. I admit I sped up slightly at the end there to force this together, but I did it. Hopefully you can forgive me because I was doing it in order to finish off that example. Okay, so this is going to go in 8 seconds. So I'm going to stop it now. I'm not going to go on because a really important rule of action hours is that when that timer goes, you strictly stop even if you're in the middle of something. By standing up and walking away for at least 10, if not 15 minutes, you are going to really reset your brain. It means whatever you come back to later is going to be much more useful. So differentiation, you've got videos number, your playlist is videos number 22, 23, 24, 25, 26. Okay, that's in the content guide, 22, 23, 24, 25, 26. That finishes off the whole of differentiation. And I hope what I've shown you today is how important the chain rule is, and that all of these topics you do at the end, implicit differentiation, parametric differentiation, and the chain rule, connected rates of change, and differentiating inverse functions, it's all the chain rule. And not only that, if you can do the chain rule without writing u equals, then when you could do integration, which is basically the chain rule, you're going to be much, much better at it. I will see you tomorrow at 1 o'clock. We will always start with integration, always. And we are going to, if I look at the schedule, it's, it's integration, brilliant. So we will do a summary tomorrow of how all the integration fits together and the ways to think about integration step by step. Okay, see you tomorrow. Enjoy the rest of your day. If you want to do a study hour to work on what your teachers have set you, then I will be here from 4 till 5. And if you want help with what your teachers have set you, then post in the TT course. And that's what I'm going to do now. After I've had my little break, I'll sit and help you out. See you later.